In this video, we're going to talk about units of concentration. And so when we're talking about concentration, basically it's just the ratio of the amount of solute within the solvent. Now, in this video, we're going through different types of units of concentration. So we're looking at different aspects of different ratios, and it's all depending on, the substance, what it's made of, the state of matter, and, just this different information, really. All right, and so we're just going to take you through just a couple of different units of concentration and how we interpret them and how we calculate them. All right, and so let's get started. All right, so there's the first type of units of concentration we're going to talk about is percent concentrations. So percent concentrations overall is just the expressed amount of solute in 100 units of solvent. All right, so how many X amount of solute do you have per 100 units of solvent, depending on whatever the units that we're talking about. All right, and so there's three different types that we're going to address in this video. First, you have the mass percent, all right, volume percent, and lastly, mass volume percent. Okay, and so first we're going to talk about the mass volume percent. Okay, so we have mass percent. All right, so mass percent is typically for solid solutions where where you have the solid of a solute in a solid solution, particularly. All right, and so mass percent is a good way for us to able to quantify how much of the solute, which is a solid, is in the solvent, which is also a solid. So here's an example. So the percentage of gold in jewelry is typically in carats, with 24 karat gold representing 100% gold. A sample of an 18 karat gold would contain 18 grams of gold and 24 grams of metal, which would equal to a mass percent of 75%. Calculate the mass of gold in 5.05 gram ring that is an 18 karat gold. All right, and so what I'm trying to figure out, if you have a ring that basically the purity of the ring is 18 carats, all right, and the ring is 5.05 grams, all right, how much or what's the mass of the gold solute that's within this this solid solution, right, within this this ring itself? All right, so let's kind of pick out what we do know, and that would potentially may help us to answer this question. All right, and so we know that the mass percent is 75%. Okay, and then you also know that it is 5.05 grams of the ring. Okay, so let's just kind of break down for us to understand exactly what is this mass percent and what is it saying. All right, and so basically it's the mass of the solute, divided by the mass of the solvent, okay, times by 100. That's what this mass percent is basically telling us. All right, and then remember, just like we said earlier, if it's for the solvent, it's per 100. In this case, it would be 100 grams. Remember, it's 100 units, but in this case, it would be 100 grams, and that would be our mass for this case, right? And so when you kind of think about what this problem is telling us, we know that percent is 75%, and then we start off with a 5.05 gram carat ring, right? And so we know this right here has to be our total solution. All right, and so remember, the solution consists of both the solute and the solvent. So together, in this case, this gold ring solution, it has a mass of 5.05. So how do we figure out how much gold do we have in there? All right, well, if this is your solution, right, then what we could do is we have 5.05 grams, and we're going to multiply it by this here. All right, and I'm just going to kind of break this down to what we have up here so that you can see exactly where we're coming from. All right, and so it's 75%. So this simply means that you have 75 grams of gold over 100 grams of solution. All right, times 100. So that's what this number is coming from, and that's how we come up with this. All right, that's your mass percentage. All right, and so we could use this, all right, in order to kind of help us out here. So then I would basically write 75 grams of gold over 100 grams of solution. Okay, and so if I put this in the calculator, it turns out in the 5.05 grams ring, there are 3.79 grams of gold. Okay, and so that's how you will use this mass percent concentration. All right, so let's look at volume percent concentration. So volume percent concentration is typically for liquid solutions. All right, so if you put two liquids together and they form a solution, we use VV percent. Okay, so for volume concentrations, basically the volume of the solute divided by 100 mils of the 100 mils of the solution. All right. And then we multiply that by 100. So this is how we typically get volume percent concentration. All right, so let's kind of look at the example. So the example below states that how many milliliters of methyl alcohol are needed to prepare 75 mils of a 0.5% volume percent concentration solution. Okay, and so let's go ahead and kind of dissect this and see what we have. And so we see that we have some amount of solution, right? And that is 75 mils. And then I tell you that we have 5.0% volume concentration. What does that mean? All right, this simply means that you have 5.0 mils of this methyl alcohol, all right, divided by 100 mils of the solution. That's what this is. And now obviously times it by 100 because it's a percent, but that's what this simply means. Okay. So now the question is, if you have 75 mils of this methyl alcohol, how much of it is a methyl alcohol solution? How much of it is actually methyl alcohol? Okay. And so we will basically take this number, all right, and you're going to multiply by this percentage here. All right. And so we'll go ahead and do that, where we have 75 mils of the solution, and we're going to multiply by 5.0 mils of the methyl alcohol divided by 100 mils of the solution. Okay, so the mils of solution is going to cancel itself out. And then so when you 75 times 5 divided by 100, you'll get it is 3.8 mils of methyl alcohol. Okay, and so hopefully you start to see that there's a pattern to all these percent concentrations, whether it be mass to mass, in this case volume to volume. All right, and the next one that we're going to look at is the mass to volume. All right, so here, mass volume percent concentration is basically the number of grams of solute as a percentage of the number of milliliters of the solution. Okay, and so here we can kind of see the equation, where it's the mass of the solute divided by the volume of the solution, thus mass to volume, right? Mass over volume. All right, and typically it's over 100 mils or 100 units of the solution, and you multiply that by 100. All right, so let me go ahead and let's go ahead and just look through an example of how we work a problem like this. A solution of heparin sodium, an anticoagulant for blood, contains 1.8 grams of heparin sodium dissolved to make a final volume of 15 milliliters of solution. What is the mass volume percent of concentration of this solution? All right, so here basically we're looking for the mass volume percent concentration. So that's what we're looking for. And remember, it is the mass of the solute divided by the volume of the solution multiplied by 100. So in this question, I tell you the mass of heparin sodium, which is 1.8, divided by the total solution that's going to be made is 15 milliliters. And then we're going to multiply this by 100. And when you do this, we get that it is 12% mass per volume percent concentration. All right, so this is the way that you would typically find this out. So let's look at another example. So how many grams of NaCl are needed to prepare 250 milliliters of a 1.5% mass volume saline solution? All right, and so let's think about what's going on here. So we're trying to figure out how many grams, all right, of NaCl that you're going to need in order to make 250 mils of a 1.5% molar volume solution. All right, and so consider the equation itself. So remember, a molar volume solution is you have the mass of the solute divided by the volume of solution, all right, times 100. So that's this, right? All right, and so let's kind of think about what is it asking for in this case, right? It's asking for the grams of NaCl that is needed to form a 250 ml solution of a 1.5. Okay, and so when you kind of think about what's given to us, is that you're trying to find, let's kind of think about what we know from this equation, right? And so I'm going to go ahead and highlight this so that we can see this. So this right here, I'm at the highlighter, all right, the grams of NaCl is basically the mass of the solute. All right, so we're basically going to be looking for this top portion here. This 250 milliliter solution, well, that's the volume of the solution right here, all right, times 100, and then it tells you the percentage, all right, and so here's our mass volume percent concentration, and so that goes right here, all right, and so all in all that simply means then we got to solve for this right here. This is what we're solving for, all right? And so I'm going to rearrange this equation so I could solve for it accordingly, all right? So the first thing I'm going to do, I'm going to divide out the 100, okay? Then I'm going to multiply out this volume of solution. So let's rewrite this. I know this looks messy, but basically it is the mass of the solute is equal to, all right, the wrong letter, mass volume percent, all right, times the volume of the solution divided by 100. Okay, and so this is our equation here. So let's go ahead and plug in the numbers accordingly. All right, and so it is the mass volume percent is 1.5 times the volume of the solution is 250 divided by 100. Okay, and then when you plug this into the calculator, we get 3.8 grams of NaCl, and that's how many grams of NaCl that you're going to need. All right, so the next unit of concentration that we're going to talk about is parts per million, parts per billion. And basically, it's a unit of concentration when the concentration is really, really, really small, okay? So the parts can be in any unit, either in mass or volume. The whole point, the most important thing is that the units have to be the same for both the solute and the solvent. All right, so you cannot have any kind of like ratio between mass and volume. It's really just mass of solute versus them, and in respect to the mass of the solution, or it's the volume of the solute in respect to the volume of the solution. So it's one or the other. All right, and so parts per million specifically is the mass or volume of the solute divided by the mass or volume. Remember, these two has to be exactly the same of solution, okay, times 10 to the 6. So that's parts per million. While parts per billion, once again, much like parts per million, mass or volume of solute divided by mass or volume of the solution. But remember, these two have to be the same. and then times 10 to the ninth. So that's parts per billion. So let's kind of look at an example problem. So let's look at this example. The maximum allowable concentration of chloroform, CHCl3, in drinking water is 100 parts per billion. What is the maximum amount in grams of chloroform allowed in a glass containing 400 grams of water? All right. And so here we have that it's 100 parts per billion, okay? And so that's basically the concentration here, right? And then we're trying to figure out how much chloroform can be allowed in 400 grams of H2O, of drinking water, okay? And so let's go ahead and just tackle this so that we could kind of see what's going on. All right, so remember from the equation I kind of showed you earlier, when it comes from parts per billion, remember parts per billion is basically where you have, in this case, it's the mass of the solute divided by the mass of the solution times 10 to the ninth. That's what parts per billion is, okay? And so when we're considering what we're given here, all right, so once again, let's kind of look at this equation here. So we have 100 parts per billion, which is equal to, remember, the mass of the solute times, we'll kind of jump over here, mass of the solution times 10 to the ninth. All right, that's parts per billion. Now, what do we know? What is given to us? Well, we know the mass of the solution. Okay, the mass of the solution is 400 grams. All right, so then that means, and what we're looking for, we're trying to figure out what's the mass of the actual chloroform. And chloroform in this case is the mass of the solute. So we're essentially solving for this here. All right, that's what we're solving for. All right, so what we need to do is rearrange this equation so that way we could effectively solve for this. All right, and so let me go ahead and let's rearrange the equation. So first thing I'm going to do, I'm going to divide by 10 to the ninth. By doing that, I cross this out here and I put it to the other side. And the next thing I'm going to do, I'm going to multiply by the mass of solution. All right, by doing that, I get it over here, and then here I could also multiply them by the mass of the solution itself. All right, and so what's going to look like, at least the equation purposes, is that you have the mass of the solution times 100 parts per billion divided by 10 to the ninth. Or other words, it's going to be 400 grams, that's the mass of the solution, times 100 parts per billion divided by 10 to the ninth. And so that's basically how we figure this out. So we multiply, divide in the calculator accordingly, and you get your answer to be about 4 times 10 to the negative fifth grams, or 0.04 milligrams. All right, either way, it works. Okay. So the last unit of concentration we're going to talk about is the one that's mostly generally used in chemistry, and it's the mole volume ratio, where we're looking at the number of moles of solute dissolved per liters of solution. And this is what we call molarity. All right, and so molarity, giant M, all right, is the moles of solute divided by liters of solution. Okay, and so this is basically the general formula for molarity. Okay, so let's kind of look into an example of how this can be used. All right, so let's look at this problem. It states, what is the molarity of a solution made by dissolving 2.355 grams of sulfuric acid in water and diluting to a final volume of 15.0 milliliters? All right, so here here's the molarity equation: moles of solute over liters of solution. Now, take note of the units that molarity must be in. All right, it's a ratio between moles and liters. Okay, and so before you can actually even use this equation, you have to make sure you have the number of moles of a substance and the number of liters of solution. All right. So if you noticed that I have 2.35 grams of sulfuric acid, so I have to convert grams to moles. And I also have 50 milliliters of solution, so I have to convert from milliliters to liters. All right. And so let's go ahead and just kind of do that by part. So the first thing I'm going to do is convert the 2.355 grams of sulfuric acid to moles of sulfuric acid. All right. And I'll use the molar mass to do that. So I have 2.355 grams of sulfuric acid. All right. So for every 1 mole of sulfuric acid, I have 98.1 grams of sulfuric acid. All right. So I put this in a calculator and I get 0.0240 moles of H2SO4. All right. And then the last part, I have 50.0 milliliters of solution. All right. And so if that's the case, then I know for every 1,000 milliliters, I have 1 liter. So it turns out to be 0.050 liters of solution. All right. And so I'm going to use these numbers, this and this, in my equation here. All right. And so if I were to rewrite this, my molarity, sorry, I didn't mean to use a, all right, so my molarity is 0.0240 moles, all right, of H2SO4 divided by 0.0500 liters of the solution. All right. And so if I do that, multiply, divide, well, really just divide, and then you'll get the answer to be 0.480 molarity of sulfuric acid, H2SO4. So that's the final answer here. So here we kind of, I know it was a longer video, but we looked at all the different types of units of concentration, and we looked at different examples of how we use this in any type of application.